Okay, so now it's 4:05. We should get started. So the agenda for today is metal semiconductor contacts. Now this is a new topic. Although it is new, many concepts you previously learned under the topic on PN junction diode would still continue to apply. Of course, there will be a couple of new concepts that will be introduced. Now, the discussion will address the following 3 points. The first point is, why do we need a metal semiconductor contact? Right, so it's important to understand the motivation behind such a structure where people put metal onto semiconductor. So in particular, what purpose does such a contact serve? Now, the second point that I will discuss is that well, it so turns out that putting a metal and a semiconductor together is not a straightforward thing at all. Now, many people will think that it is something very straightforward because individually, a metal and a semiconductor are both resistors, right? They obey Ohm's law. And if we put them together, we just get another resistor which obey Ohm's law. All right, but it turns out that the outcome is not so straightforward. It all depends on what kind of interaction that takes place between the metal and the semiconductor when they are in contact. All right, so that will be the third point that we are going to address. Okay, so let me start. Okay, metal semiconductor contacts are very important practically because from a semiconductor device point of view, we need to form metal contacts in order to make connection to external circuit. Like for example, if you have a PN junction diode, as you know, both regions are semiconductor, the P region and the N region both are semiconductors. So how do we make contact to an external circuit? For example, connecting the diode to a supply voltage source that allows you to either forward or reverse bias the PN junction diode. Now, in order to do that, we need to build metal contacts on the semiconductor. Okay, so one of the purpose of such metal semiconductor contacts is to allow the semiconductor device to be connected to another part of the circuit. Now, it so turns out that it's not a straightforward thing to put metal onto semiconductor. And we do not always get a simple metal semiconductor contact that obeys Ohm's law. In fact, it turns out that we will get two types of metal semiconductor contact. The two types of contact are called Schottky contact and ohmic contact. Now, Schottky contact is an outcome that is pretty much surprising because a Schottky contact is also known as a rectifying contact. In other words, it has a behavior similar to that of a PN junction diode in the sense that it allows current to flow only in one direction and it blocks current flow in the opposite direction. So why do we get such a contact? By putting a metal onto a semiconductor, right? So we will learn the theory behind this. Now, a Schottky contact is also called a Schottky diode simply because of its behavior, electrical behavior, right? Blocking current in one direction, but allowing current to flow in the other direction. Now, the other contact is quite expected, and we call this ohmic contact. Ohmic contact is just a resistive contact, right? Given the fact that both metal and semiconductor are resistances or resistors themselves, so putting or connecting them together, we just get another resistors, okay? Now, ohmic contact are important in connecting semiconductor devices to other parts of the circuits. So ohmic contact allows current to flow freely in both directions.
So your mic is muted.
Was it accidentally muted?
Should be.
So it was okay in the beginning, right?
Yes.
Okay, okay. Maybe I accidentally muted it. Sorry. Okay, coming back, I don't know which part is affected, so maybe I just quickly go through Schottky contact again. It is a rectifying contact, so it has similar electrical behavior as a diode, right? So sometimes a Schottky contact is also called a Schottky diode. Now, the other type of contact is pretty much an expected outcome, which is called the ohmic contact. Now, ohmic contact is needed to connect a semiconductor device to other parts of the circuit. And the objective in forming an ohmic contact is that the resistance of the ohmic contact must be very low. And the contact must allow current to flow easily in both directions with very low resistance in both directions. Okay, so let's see what happens when we put a metal onto a semiconductor, why the outcome can be unexpected sometimes. Now, in order to understand that, I need to introduce some new concepts or terminologies, right? And first of all, I want you to focus on the diagram on the right. Now, the diagram on the right should be quite familiar to most of you by now. It is the Venn diagram of an N-type semiconductor. So how do I know that the semiconductor is N-type? The Fermi level appears to be closer to EC than EV. All right, so it is an N-type semiconductor. Now, there are two new parameters here that you need to take note, which were previously not discussed. The first one is denoted by this notation Q chi. This is not X, but chi, C-H-I, pronounced as chi. Now, Q chi is called electron affinity. Now, electron affinity is a term that some of you who are taking chemistry might have come across. So electron affinity simply refers to how strongly a given material attracts electron. Okay, so it is defined as the energy difference between the vacuum level. I think most of you know what a vacuum level is. It is a level denoting a free electron, free from the influence of the material, right? So the electron affinity is defined as the energy difference between the vacuum level and the conduction band EC. Now, why do people define it like this? As you know, most electron exist at the bottom of the conduction band. So in order to remove an electron from the semiconductor, right, from the conduction band of the semiconductor, and such that the electron now becomes free from the material, it is no longer under the influence of the material, the energy that we need to provide will be given as the difference between the vacuum level and EC. Okay, so this is electron affinity. Now, the other parameter that you need to understand is work function, right? For semiconductor, the work function is usually denoted as Q phi S. S denotes semiconductor. So what is the meaning of work function? Well, the work function is defined as the average energy that is needed to remove an electron from the material. Now, sometimes it is confused with electron affinity. Okay, so let's clear this thing up. Now, for electron affinity, it tells us the energy that you need to provide to remove an electron from the conduction band of the semiconductor. All right. Now, in work function, it refers to the average energy that you need to provide in order to remove an electron from the material itself. So in other words, in the case of work function, the electron that you remove could come from the conduction band or the valence band. But of course, in this example here, if you want to remove an electron from the N-type semiconductor, most likely the electron that you remove will come from the conduction band. But there is a non-zero probability that the electron could also come from the valence band, although the probability is much smaller. Okay, so the work function of a semiconductor is defined in a different way from the electron affinity. Okay, so the work function is defined as the energy difference between the vacuum level and the Fermi level. All right. As you know, the Fermi level gives the average potential energy of electron in the semiconductor. Right, so that provides a good reference for measuring the average energy that one has to provide in order to remove an electron from the semiconductor. Okay, so these are the new parameters that you need to get to know them now. So let's move to the band diagram on the left. Now the band diagram on the left shows you the energy band diagram of a metal, which is different from that of a semiconductor in the sense that you do not see the EC and the EV. The reason is because in the metal, there is no band gap. All right, so the consideration of EC and EV becomes irrelevant. In the metal, there are many electrons. The electrons are filled right across a continuous distribution of energy levels. Okay. Therefore, in drawing the energy band diagram of metal, we don't draw EC and EV. Instead, we only draw one line, which is the Fermi level of the metal, EFM. Okay. Now, the Fermi level of metal has the same meaning as the Fermi level in the semiconductor. It gives you the average potential energy of electrons in the metal. Right. Its original definition is that at the Fermi level, the probability of finding an electron is 50%. Now, for energy level above the Fermi level, this probability drops to 0 very quickly. So in other words, for energy level above the Fermi level, they are mostly empty. They are not filled by electrons. On the other hand, for energy level below the Fermi level, the probability of finding an electron goes to 1 very quickly. Right? So therefore, for energy level below the Fermi level, the energy levels are usually filled. Okay, so this is represented by this shaded region here, showing that all the energy levels below the Fermi level are filled. All right, so in the case of metal, the work function is defined like this. Okay, in a similar way as the energy difference between the vacuum level and the Fermi level. In fact, the concept of work function is more intuitive in the metal. As what I mentioned just now, in the case of metal, the electron field energy levels all the way up to the Fermi level. And above the Fermi level, the energy levels are mostly empty. Okay, so if you want to remove an electron from the metal, this electron would most likely come from an energy state that is near the Fermi level. Okay, so that's how the work function is defined for metal. Okay, so with this in mind, we can then try to understand what happens when a metal is placed in contact with a semiconductor, right? Which is what we are going to discuss next. Before that, a summary of what I have discussed, all right? So you need to get to know some of the new terminologies related to the new concepts. I think vacuum level, as I mentioned earlier, is quite familiar to most of you by now. All right, so Fermi level as well. And what are new here would be the work function of the metal, the work function of the semiconductor, and the electron affinity. Okay, just take note of how they are defined and also the units for these parameters. They are all expressed in electron volts. Okay, of course, it can be converted to volts simply by dividing the value by the electronic charge Q. Okay. Now, let's try to understand what happened when the two materials come into contact. Now, the concept here is not new. In fact, I introduced this concept earlier. When two different materials come into contact, charge transfer between the two materials will happen. All right. The reason is very simple because if you take any two materials, generally the Fermi levels will not be at the same level at the beginning. Okay, like for example, in material A, we could have a case where the Fermi level is higher than in material B. So what it means is that in material A, electrons are filled to higher energy levels than those electrons in material B. Okay, so when you bring the two materials into contact, what essentially happens is that at the very instant of contact, those electrons that are filled at higher energy level in material A will see a lot of empty energy states in material B. So they readily get transferred across to material B. All right. But of course, in the process of transfer, a potential difference between the two materials will be established, and the potential difference will basically oppose the transfer, all right, such that at thermal equilibrium, okay, the net transfer becomes 0, and that is the point also when the two Fermi levels are aligned, okay, so that there is no difference in the probability of electron occupying any energy states in the two material at thermal equilibrium. All right, so this is a concept that I introduced when we discussed p-n junction earlier. So the same concept can be applied in this case in a metal semiconductor contact. All right, now maybe before going further, it might be useful to also explain why we need to introduce a new concept called the work function. Now, as you know, in the past, since from part 1 onwards, you have learned how to calculate the position of the Fermi level in the band gap. All right, because a semiconductor has a band gap, so if the doping concentration is known, we can quantify the position of the Fermi level within the band gap, either with reference to EC, to EV, or even to EI, the center of the band gap. However, in the metal, there is no band gap. So there will be difficulty in quantifying the position of the Fermi level because we cannot find a convenience reference level in the metal, all right? Unless we introduce the concept of work function, because work function uses the reference level or the vacuum level as the reference level. Okay, so if we know the work function of the metal, then we know the position of the Fermi level in the metal. And by the way, the work function of a metal or a semiconductor can be measured using an experiment called the photoelectric experiment, all right, which was first pioneered by Albert Einstein. So in the photoelectric experiment, is a very simple experiment, right? We shine light onto the material, which we want to measure the work function. All right, so if the wavelength of the light is not suitable in a sense that the photon energy of the light is less than the work function, then the light cannot liberate electrons from the material. So as you vary the wavelength, you also vary the energy of the photon. So there will be a particular point where the photon energy just become equal to the work function of the material. And beyond that, then the light can easily free electron from the material, and the electrons that are liberated can be detected as a current flow in an external circuit. Okay, so there's a photoelectric experiment which give us the information on the work function of a material. Okay, let's move on to understand why or what happens when a metal and a semiconductor are placed together. So in this example, we are looking at an N-type semiconductor, okay, whose work function is assumed to be smaller than that of the metal. Okay, so imagine what happens when these two materials are in contact at the very initial instance, when they come into contact. Because the Fermi level in the semiconductor is higher than that in the metal, we have more electrons occupying higher energy states than those in the metal. So in the metal, the electrons are filled up to this level, whereas, as you know, in an N-type semiconductor, many electrons are found, right, in the conduction band. So obviously, when the two materials are put into contact, the electrons in the conduction band of the semiconductor will see all the empty states in the metal, and they readily get transferred across, okay, to the metal. So this charge transfer will result in the semiconductor becoming net positively charged and the metal becoming net negatively charged because the metal receives electrons and the semiconductor loses electrons. Okay, now the positive charge in the semiconductor is actually due to the space charge coming from the ionized donor impurity atoms. So this concept here is the same as the concept we discussed in p-n junction, Remember, imagine now the metal is the p-type semiconductor. So when you put them together to form a p-n junction, electron diffuse from the n to the p, and the diffusion, right, of the electron will leave behind a space charged region consisting of the ionized donor impurity atoms. All right, so the same situation exists here. So after electrons left the n-type semiconductor going to the metal, after they have gone to the metal, all right, what would be left near the junction here are the ionized donor impurity atoms. So that forms a positive charge inside the semiconductor. And the electrons they are transferred across to the metal, right, will cause the metal to become negatively charged. And these electrons are held near the interface or near the contact here by the positive charges inside the semiconductor. Okay. But more importantly, you should realize that this transfer of charges will result in a potential difference between the two material and also a built-in electric field being formed, right, across the metal semiconductor contact. Now, the built-in electric field serves the same purpose as the built-in electric field in the PN junction diode. It serves to oppose the transfer of electrons from the semiconductor to the metal. Right, so it works like this. So as more and more electrons are transferred from the semiconductor to the metal, the built-in field also gets stronger and stronger. So the resistance to the transfer also gets stronger and stronger. So eventually, when the built-in electric field gets large enough such that it totally opposes the transfer of the electrons from the semiconductor to the metal, then thermal equilibrium is established, right? And the Venn diagram of the metal semiconductor contact at thermal equilibrium is shown here. All right. Okay. So at thermal equilibrium, the two Fermi levels are aligned, right? Denoting that the net transfer of charges across the contact is 0. And the Venn diagram on the semiconductor side is drawn like this. So let's try to understand why the EC bends upward like this compared to the rest of the semiconductor region. One way to understand that is to look at the direction of the built-in electric field. So it's quite clear that in this case, the built-in electric field actually points from the N-type semiconductor towards the metal. Or if you take reference with respect to the positive x-axis, we can say that the electric field in this case is a negative electric field. Now, as you know, electric field in a semiconductor can be related to the gradient in the energy band diagram. All right, so since the electric field is negative, then the gradient in the energy band diagram with respect to the positive x-axis is a negative gradient. So in other words, this part of the energy band must bend upwards like this to give you a negative gradient in EC and EV, as well as EI, which is not drawn here. Okay, all right. So there's one way to understand why the energy band bend upwards like this near the contact region here. Now there's another way to understand this. Because the N-type semiconductor has lost electrons, right? So the electron concentration near this region or within this region will be lower than the rest of the N-type semiconductor region. So since the electron concentration within this region is lower, all right, the separation between the Fermi level and the conduction band HEC will be larger here than the rest of the semiconductor region. All right, so that is why the band must bend upwards to give you a larger difference between EC and EFN compared to the rest of the semiconductor. Okay, so there's another way to self-consistently understand why the energy band bend upwards like this. Okay, all right. Now, due to the transfer of charges, as mentioned earlier, there will be a voltage difference set up between the two material, and this is none other than the built-in voltage. And in this case, the built-in voltage is denoted as QV0, right? And it can be evaluated by taking the difference between the two Fermi level at the beginning of contact formation. So at the beginning of contact formation, the Fermi level are at their respective original positions. So in the case of the N-type semiconductor, it is here, right? And in the case of metal, it is here. So to calculate the difference between the two Fermi level, we can simply take the difference between the two work functions, because the reference level is the same in both cases, which is the vacuum level. Okay, all right. So that's how we evaluate the built-in potential, right? Which is just the difference between the two work functions. Okay, now all right, I think you should by now know the purpose of the built-in voltage is the same as the built-in field, right? Is to oppose or present a potential barrier to the electrons in the N-type semiconductor, preventing them from going over to the metal. Okay. Now there's a new parameter here again. All right, there's a new parameter, so please take note. We call this the Schottky barrier. And by the way, this kind of contact that we obtain from this example is called a Schottky contact. I will come to explain why this contact has a rectifying behavior later on. Okay. All right, so there's a new parameter here, Q5B, is called the Schottky barrier. So how is the Schottky barrier defined? It is defined as the difference between the metal work function and the electron affinity of the semiconductor. In other words, it is simply the difference between the Fermi level in the metal and the conduction bandage of the N-type semiconductor. Now, the importance of Schottky barrier will be more easily understood later on when we talk about forward and reverse biasing of the Schottky contact. But essentially, the Schottky barrier prevents electrons in the metal going to the N-type semiconductor. It presents a potential barrier. Right, so in order for electrons in the metal to go to the N-type semiconductor, the electron in the metal must overcome this potential barrier. Okay, so this is a new parameter that you need to pay some attention to. Now, of course, we have a space charge region within the N-type semiconductor due to the departure of the electrons. We now get a space charge region. So the W here is the width of the space charge region. Since we are considering thermal equilibrium, this W actually also represents W naught. Right, the zero here is not shown. But essentially, this W shows you the thermal equilibrium width of the space charge region. Okay, all right. So why is this a contact? Why is this contact rectifying? Right, why is this a rectifying contact? We will soon look into that. So let's just recap, right, quickly what we have discussed. So essentially, it is the difference in the Fermi level that drives the transfer of charges between the two materials. All right, so based on this example, charge or electrons are transferred from the N-type semiconductor to the metal. Okay, because at the very beginning, electrons in the conduction band of the semiconductor are found at a higher energy level than those electrons in the metal. Okay, so electrons in the semiconductor can get to the metal very easily at the very instant when a contact is formed. Okay, because they face no barrier. Now, as they go to the metal, then a built-in voltage will be developed across the contact, right? And that will slow down the transfer. Now, why electrons in the metal cannot go to the N-type semiconductor? Because they are blocked by the Schottky barrier. Okay, so as a result, at the very beginning when a contact is formed, there is a net transfer of electrons from the semiconductor to the metal. But as I mentioned just now, with the N-type semiconductor losing electrons, it will become net positively charged because the uncompensated donor ions will now start to appear, right, forming a space charge region. Okay, and that will tend to oppose the transfer of the electrons. Okay. Similarly, electrons that flow into the metal that get transferred to the metal will get accumulated at the metal surface as a layer of surface charge. They are held by the positive space charge in the semiconductor side. Okay, so the semiconductor becomes positively charged and the metal becomes negatively charged. Now keep in mind that the positive charges in the semiconductor are the uncompensated donor ions. They are not the holes. Huh? Right, so don't make this mistake. Well, in fact, I've already clarified this right at the beginning when we talk about the p-n junction. Okay, so the electric field and the band bending inside the semiconductor are similar to that of a p plus n junction. Now, how to understand this statement? Okay, first thing you need to realize that in this example, the depletion region is only found in the n-type semiconductor. There is no depletion region in the metal. Now, if you understand or if you can observe this, then you should recall what happens in the p-n junction if I dope the p side heavily with respect to the n, right? From space charge neutrality consideration, if you may recall, from space charge neutrality consideration in such a p plus n diode, all right, most of the space charge region exists in the n semiconductor region or the lowly doped n region. Okay, all right, so this example that we have here is very similar to the p plus n p-n junction diode, where most of the depletion region exists in the n region with negligible depletion region inside the metal. Okay, right? So therefore, we don't have to go back and re-derive all the equation again. We can borrow the expression for W for the p-n junction. This is the simplified form. If you may recall, okay, I don't know why this bar here is blocking. Okay, never mind. It's not so serious here. So if you may recall, the depletion width W of a p-n junction is given by this expression, where this term here is Q, this is Na, this is Nd. Okay. Now, since the metal semiconductor contact that we are discussing here is very similar to the p plus n junction, right? So we can assume that the Na term to be much bigger than the Nd term, right? And therefore we can neglect the 1 over Na term, all right, and apply the result to this metal semiconductor contact. So this is the depletion width, all right, for this metal semiconductor contact. Okay, all right. So I hope you get the point that I'm trying to make here. Okay. Now, since there is a space charge stored at such a metal semiconductor contact, there is a junction capacitance associated with this metal semiconductor contact, and the junction capacitance can be evaluated using the same expression as we derived earlier for a semiconductor, right? Which is the permittivity of the semiconductor times the area of the contact divided by the width of the space charge region, right? This expression is used earlier when we talk about the junction capacitance of a p-n junction. Okay. So in applying this, we just need to evaluate W according to equation 1. All right. Now, why is the junction capacitance equation similar to that of a parallel plate capacitor? The explanation is of a p-n junction. Now, imagine I change the voltage across the metal semiconductor by a small amount, right? The change in the charge will happen at the edge of the space charge region in the semiconductor side, and the change in the charge in the metal will happen right at the interface here. Okay, so you have a sheet of charge here and another sheet of charge here. They are separated by a certain distance, which is the W, right? The width of the space charge region. Okay, right? So I mentioned this earlier when we discussed the junction capacitance. So the positive space charge in the semiconductor and the negative electronic charge in the metal results in a potential difference, which we call the built-in potential, right, between the two material. And note that the potential is higher in the semiconductor side, all right, as compared to the metal side. Okay, right. So this is similar to the built-in potential of a p-n junction, when the n region is more positive compared to the p region. Okay, right. So due to the PD or the potential difference developed, all right, electrons flowing from the metal will now encounter a potential barrier, which is QV0 or QVBI. All right, so QVBI will stop the flow of electrons from the semiconductor into the metal when thermal equilibrium is achieved. Okay, all right. All right, just to reinforce again, right, equation 2 shows you how the calculation of the built-in potential for this metal semiconductor contact can be calculated, right? We just need to take the difference between the two work functions, which essentially give us the difference between the two Fermi levels at the beginning when a contact was formed. Okay. Yep, equation 3 shows you the Schottky barrier expression. This can be very important later on when we discuss reverse bias. All right, Schottky contact plays a very important role in limiting the current that flows under reverse bias. So I will elaborate more later on. All right, Schottky barrier sometimes is also called the Schottky barrier height, right, with just the additional word height. Okay. This statement is similar to what I've been saying for the past few minutes. So the energy barrier refers to the built-in potential barrier, right? That is formed discourages electron flow, right? Okay, can also be interpreted in terms of the electric field that develop across the contact. All right, this is none other than the built-in field, which opposes the flow of the electron from the semiconductor to the metal. Okay, so at this point of the discussion, I hope you realize that the metal semiconductor contact that we have here is very similar to a P plus N PN junction diode. Right, so it's not surprising later on when I tell you that this metal semiconductor contact is rectifying. In other words, it allows current to flow in one direction, but it blocks the flow of current in the other direction. Okay, so let's see what happens when we forward or reverse bias this particular metal contact example that we are looking at. Now, just a note here, all right, the discussion for this example, for this particular Schottky contact is very similar to that of a PN junction and also a P plus N junction in particular. Okay, so many of the concepts that we learn for PN junction theory or P plus N one-sided diode can be applied in this case. But there are some differences, of course, which I'll mention later on. Okay, so as you know, in the PN junction, the built-in voltage or the built-in potential barrier or the energy barrier can be modulated. All right, can either be increased or decreased depending on the external bias that you apply. Right, so this is what we are going to discuss next. Okay, so let's see what happens when the Schottky contact is subjected to an external voltage. So let's consider the case of forward bias. There are only two possible ways of applying an external voltage because this contact is also a two-terminal device. So one way is to apply the positive voltage to the metal, all right, with respect to the N-type semiconductor. Right. So in this case, we call this manner by which we apply the voltage as forward biasing or forward bias. So we'll see why we call it forward bias, because the current that flows across the contact is large. Okay, all right. Now there's one point that you need to take note here, which is similar to the point I mentioned for PN junction. Now, because the depletion or space charge region has a very high resistance compared to the metal and the semiconductor, right? So most of the external voltage that you apply will be dropped across the space charge region. All right, so in our discussion, we will assume negligible or zero voltage drop across the metal, which is quite reasonable because, as you know, metal has very low resistance, so the voltage drop across the metal is negligible. Now, we will also neglect the voltage drop across the neutral N semiconductor region. In other words, the region outside the space charge region. All right, so in this region, it is N-type doped with a high concentration of electrons, so its resistance is, although not as as low as that of a metal, but it is much lower than the resistance of the space charge or the depletion region. And I just want to recap why the depletion region has the highest resistance, because the depletion region has the lowest electron concentration in this case among the three. Okay, right. Now, in forward bias, when you apply a positive voltage to the metal, the direction of the applied electric field will point from left to right, the more positive side to the more negative side. That is the direction of the electric field, applied electric field. If you countercheck this direction against the direction of the built-in field, they oppose each other, and therefore the net electric field across the contact is reduced. All right, so this concept is the same as that of a PN junction under forward bias. No difference, okay? Then how do we draw the Venn diagram of the contact under forward bias? All right, again, quite similar to the way we draw the Venn diagram of a PN junction diode, but of course, in this case, we have a metal on this side, we have a semiconductor. Now, since the metal is biased positively, therefore, the Fermi level or the Venn diagram on the metal side is lowered with respect to the Venn diagram on the semiconductor side. Okay, how much is the lowering of the Fermi level in the metal with respect to the Fermi level in the semiconductor? It depends on the applied voltage itself, QV. Okay, so this applied external voltage, which opposes the built-in voltage V0, therefore will result in a smaller potential barrier across the contact. And the new potential barrier is simply evaluated as QV0 minus QV. Okay, in this case, right? So obviously now with a smaller potential barrier, right, electrons in the N-type semiconductor region can easily be injected into the metal. Right, as you know, N-type semiconductor has a relatively high concentration of electrons. So therefore, under forward biasing, a large current can flow across the contact. All right, so take note. Okay, so this will lead to a forward current flowing from the metal to the semiconductor. Remember, when electrons are injected from the N-type semiconductor to the metal, the direction of the current flow is actually from the metal to the N-type semiconductor based on definition. Okay, the flow of current is always defined to be the flow of positive charges. Okay, so it's opposite to the movement of the electrons or the injection of the electrons. Okay. Okay, so what happened under reverse bias? Actually, there would be some discussion later on since the diagram is shown here. So I will discuss what happened under reverse bias. All right. So what we do under reverse biasing is that we apply negative voltage to the metal with respect to the N-type semiconductor. So how do we draw the Venn diagram? So what we need to do here is to move the Fermi level of the metal upwards relative to the Fermi level in the semiconductor. How much do you move it up? It depends on the applied voltage. Okay, all right. Now, obviously, in this case, since the applied voltage reinforces the built-in voltage, all right, the net potential barrier or the barrier height at the across the contact is now larger than that at thermal equilibrium. Okay, so this new potential barrier height is QV0 plus QVR. Okay, and VR is positive under reverse bias. Okay, so the net contact potential is now larger. So obviously, electrons in the N-type semiconductor cannot go to the metal because they were already blocked under thermal equilibrium by the built-in potential, and now you're enhancing the potential across the contact, all right, by an additional amount QVR. So therefore, the electrons in the N-type semiconductor will remain blocked, right? They cannot go to the metal side. Now, the electrons in the metal also cannot easily cross into the N-type semiconductor, although the direction of the electric field may favor their movement. Remember, In this reverse bias case, we make the N or the N-type semiconductor side more positive with respect to the metal. All right, so from this alone, all right, you may tend to think the electrons in the metal could easily go to the N-type semiconductor, but they cannot because of the Schottky barrier. So the Schottky barrier present a resistance to those electrons in the metal when they try to get into the N-type semiconductor. Right. So generally under reverse bias, we will expect the potential barrier height on the semiconductor side, which is this one, to be larger than the Schottky barrier on the metal. So that's why people often say that under reverse bias of a Schottky contact, in this case, it is the Schottky contact that limits the flow of current. Right. So it is this contact that determines how successfully electrons can overcome this barrier and get into the N-type semiconductor. If the Schottky barrier is small, then more electrons in the metal can easily cross into the N-type semiconductor. On the other hand, if the Schottky barrier is large, then obviously fewer electrons can go to the N-type semiconductor, and therefore the leakage current will be lower than the previous case when the Schottky barrier is small. Okay. So from this discussion, it should be clear now that this has a diode behavior, right? Where current can flow easily in one direction and it is blocked in the other direction. So if you plot the I versus the I being the current versus V, the voltage that you apply externally across the metal semiconductor contact, the curve that you get is similar to that of a diode. So under forward biasing, as the forward bias is increased, the current will rise very rapidly, exponentially. On the other hand, if the voltage is reverse biased, then the current becomes saturated at some level because this current is now limited by the number of electrons in the metal that can successfully overcome the Schottky barrier and get into the semiconductor side. So this is a difference. I hope you notice that. All right, from this discussion, there is a major difference. Although some concepts are very similar, there is also a major difference. All right, remember, in the PN junction under reverse bias, we have minority carrier extraction across the junction. All right, it is the extracted minority carriers that are responsible for the leakage current flow under a reverse bias or in a reverse bias PN junction. All right, on the other hand, in the Schottky contact, in this example, there are no minority carrier extraction. All right, instead, it is the Schottky barrier that prevents the electrons, which are majority carriers actually in the metal, right? Prevents the electrons in the metal. The Schottky barrier prevents the electron in the metal going across to the N-type semiconductor. Okay, so this is the difference, right, between the Schottky contact and the PN junction diode. Now, another difference is related to the forward bias, right, which I forgot to mention just now, but actually, well, you should have realized it. Under forward bias, we have electron injection from the N-type semiconductor into the metal, but we do not have hole injection from the metal to the N-type semiconductor. Because this is a metal, this is not a semiconductor, right? Okay, right. Now, because of this, maybe I should talk about this later, but I just want to briefly mention this. Since holes are not injected from the metal to the N-type semiconductor, there are no excess minority carrier charge stored in the N-type semiconductor. Now, if you remember, the storage of excess minority carrier charge in the quasi-neutral region of a semiconductor in the case of PN junction will give rise to the storage capacitance. Right, remember the storage capacitance is the one that limit the turning on and turning off speed of a PN junction diode. We discussed this last week. All right, so since there is no storage capacitance in this case, a Schottky contact or a Schottky diode can switch on and off much faster than the case of a PN junction. Okay, right. I'll come to that again. Okay, so this is the reverse bias case, which I have already discussed. So let me quickly go through the slide. Okay, so under reverse bias, the potential barrier height is enhanced. So that blocks electrons in the metal, preventing them from going to the that blocks electrons in the N-type semiconductor, preventing them from going to the metal. Okay. On the other hand, all right, electrons in the metal also face a barrier going to the semiconductor. All right, this barrier is called the Schottky barrier, and therefore the current that flows under reverse bias is typically quite small. Okay, all right, so it is the Schottky barrier that determines the leakage current under reverse bias condition. Now, recall that the Schottky barrier is fixed once the material you choose to form the metal semiconductor contact are determined. All right, because the Schottky barrier is determined by the work function of the metal and the electron affinity of the N-type semiconductor. Both are basic material properties. They don't change with doping and so on. Okay, so once the materials are fixed, the Schottky barrier is fixed, and that will determine the amount of leakage current you get for that particular type of Schottky contact or Schottky diode. And notice that the leakage current is also independent of the applied voltage. Okay, simply because the Schottky barrier is unaffected by the supply voltage, by the external voltage that you apply. The external voltage that you apply only modulates the potential barrier on the semiconductor side, this side here. Okay, right? It does not change the Schottky barrier. Okay, so that's why the leakage current is actually constant in this case. Okay, right. Now you may want to recall that under reverse bias, the leakage current across the PN junction and ideal PN junction is also constant, right? That's why we call it the reverse saturation current. All right, so you should try to recall what is the underlying reason. Okay, well, obviously in the case of PN junction, the concept of Schottky barrier height does not apply. Okay. Okay, so let's move on. Right. So we are not going to re-derive everything all over again. So since the behavior of a Schottky diode is quite similar to that of a forward bias PN junction diode or reverse bias PN junction diode, we can just use the equation we obtain or we derive under the chapter on ideal diode equation. Okay, all right, the exact form. All right. However, some of the parameters are not the same, and one of them is actually the expression for I naught. Right. So in this case, the expression for the reverse saturation current is different, simply because the underlying physics that determine this reverse saturation current in the case of Schottky contact or Schottky diode is totally different from that of a PN junction. Okay. All right. So although the equation is the same, the IV equation is the same as that of PN junction, but the expression for I naught is different. Right, it is given as A, which is the area of the diode or the cross-sectional area of the diode, all right, times A star star. Now A star star is called the Richardson constant. Okay, it is a constant of proportionality that is determined by the material that forms the contact, the type of metal and the type of semiconductor you choose. Okay, now there's a temperature term here, T square. All right, and there's an exponential term here. Now in the exponent, there is the Schottky barrier, and in the denominator, we have another temperature term. Okay, it's not surprising why the reverse leakage current is temperature dependent in this case, because if you go back to this diagram here, all right, at higher temperature, the electrons in the metal become more energetic, all right, and therefore the likelihood of them overcoming the Schottky barrier to get to the semiconductor side is increased. So the leakage current all right, of a Schottky diode or Schottky contact is temperature dependent, right? It will increase with temperature, right? So that explains the temperature term here, okay, right? And this is a Schottky barrier which modulates the flow of current, all right? And since the Schottky barrier is fixed for a given set of material, metal and semiconductor, that's why I naught is a constant at a given temperature. Okay. Now, I also mentioned about practical diode being not able to follow exactly the ideal diode equation. Now, similarly, in the case of a Schottky diode, in a practical Schottky diode, the IV curve does not fit exactly the ideal expression. Okay, because there are some deviations or there are some effects that are ignored when we derive the ideal diode equation, if you still recall. Okay, all right. So in order to capture the deviation, what people do is that they introduce an additional parameter into the denominator term here. All right, this parameter n is called the ideality factor. Right, it has the same name as that of a p-n junction. All right, it gives a measure of the departure of the IV curve from an ideal behavior. Right, so if n is 1, then the IV behavior is ideal. It follows exactly the same expression as the ideal diode equation. Okay, now usually in the practical diode, n varies from 1 to 2. Okay, and the value of n also increases with the doping density of the semiconductor due to secondary effects coming in. Okay, all right, so just take note of this n, ideality factor. Okay, now at this point it's good to summarize the comparison between the Schottky diode and the p-n junction diode. All right, since during the discussion we have mentioned many similarities and also some major differences. So one of the major differences would be that a Schottky diode is a majority carrier device. So why do people call a Schottky diode a majority carrier device? If you go back to the forward bias case, we only have electron injection from the semiconductor, N-type semiconductor to the metal. Electrons are majority carriers in the N-type semiconductor. After they are injected into the metal, they are still majority carriers. Okay, and there are no hole injection from the metal into the N-type semiconductor. So in other words, in the Schottky diode, no minority carriers are involved, right? And therefore, um, we call the Schottky diode a majority carrier device. Okay, as the conduction of current is mainly determined by the majority carriers. Okay, in the forward bias, but in the reverse bias, the current is also determined by the electrons in the metal, which are also the majority carriers. Okay, so this is in contrast to a p-n junction, which is often called a minority carrier device. So why do people call p-n junction a minority carrier device? If you recall what we discussed a few weeks ago, under forward bias, you have carrier injection. So when majority carriers are injected from one region to the opposite region, they become the minority carriers. And the flow of current across the p-n junction is actually determined by the diffusion of the minority carriers. Okay, not the majority carriers. It's controlled by the diffusion of the minority carriers. Okay, so similarly under reverse bias, in the case of p-n junction under reverse bias, you have minority carrier extraction, and in the end, the leakage current that flow across the reverse bias p-n junction is determined by the diffusion of the minority carriers. Okay, right? So this is a major difference, right? So a Schottky diode does not have any minority carrier pileup. All right, in the example that we just saw, all right, so since there are no hole injection from the metal into the N-type semiconductor, we do not have storage of minority carriers inside the N-type semiconductor, and therefore the Schottky diode has no charge storage capacitance. This is a very important advantage over a PN junction. Remember, in a PN junction, it has storage capacitance. Therefore, since a Schottky diode has no storage capacitance, there is no delay related to the build-up and removal of minority carriers, unlike in the case of PN junction. So this doesn't apply, right? The charge storage capacitance does not apply to a Schottky diode. And therefore, a Schottky diode can turn on and off more quickly compared to a PN junction diode. Now, at this point, do keep in mind that there is no storage capacitance, but there is still junction capacitance due to the space charge. Okay, so when you change the voltage across a Schottky diode, the width of the space charge region has to change. So there is still a capacitive effect, but from the calculation that we did for PN junction, you will see that under forward bias, it is the storage capacitance that really determines the entire capacitance of the PN junction, right? So since there is no storage capacitance in the case of a Schottky diode, therefore, all right, the Schottky diode can turn on and off much more quickly compared to a PN junction, and therefore a Schottky diode is usually preferred for high frequency application. High frequency meaning that in the circuit, the diode is required to turn on and off at very high frequency, at very high speed, right? Many times per second, okay? All right, so how are metal semiconductor contacts made? It's quite easy actually to make a metal semiconductor contact. Is in fact easier than to fabricate a PN junction. All we need to do is just to deposit a suitable material onto a clean semiconductor surface and then pattern the metal to give a certain area, which will determine the area of the Schottky diode. That's all. Right, it's in fact much easier than forming a PN junction. If you may recall, I briefly discussed how a PN junction is formed or fabricated earlier. It's through counter-doping semiconductor region. Right, if you start with an N-type semiconductor, you need to counter-dope a certain region to make it P-type. And in the process, there are a few patterning steps that need to be executed. And these are all not necessary. Or not necessary in the case of a Schottky diode. Okay, so the fabrication is simpler, and therefore these devices can be packed more closely together. All right, and therefore they present a major advantage over the PN junction counterparts. Okay, all right. Okay, so this is the discussion for N-type Schottky contact. Okay, so to recap, if you want to form an N-type Schottky contact, the metal that you choose must have a work function larger than the N-type semiconductor. Okay, all right. In other words, the Fermi level in the metal must be lower than the Fermi level in the N-type semiconductor to give you a Schottky diode on an N-type semiconductor. Now we can also form a Schottky diode on a P-type semiconductor. Okay, so let me quickly go through the idea behind the P-type Schottky contact before we go for the break. The same concepts can be applied. Now, in order to form a Schottky contact on a P-type semiconductor, the work function we choose for the metal should be smaller than the work function of the semiconductor. In other words, to begin with, right, the Fermi level in the metal has to be higher than the Fermi level in the P-type semiconductor. This is important because when the two materials come into contact, right, electrons will be transferred from the metal to the P-type semiconductor. All right, so due to this electron transfer, okay, the metal will become positively charged. All right, if you look at this diagram where my cursor is, so the metal will become positively charged. And since the P-type semiconductor gains electron, it will become negatively charged. But notice the nature of the negative charge here these negative charges here are not electrons. So what happened to the electron? Right, it's quite easy to visualize. So imagine now these two materials come in the contact. So there are many electrons filled to higher energy level than the holes in the p-type semiconductor. Remember, holes are empty energy states. So at the moment of contact, these electrons filled at higher energy level are readily transferred to the holes in the p-type semiconductor. In other words, the electron that get transferred from the metal to the semiconductor, you can literally think of them recombining with the holes in the p-type semiconductor, removing the holes. So since holes are removed from the p-type semiconductor, what you get in the p-type semiconductor will be a space charged region comprising negatively charged acceptor ions. So the negative charges that you see here are negatively charged acceptor ions, because the electrons that get transferred here have recombined with the holes, exposing the uncompensated negatively charged acceptor ions in this case. Okay, all right. Now, due to the charge transfer, we have a built-in electric field. The built-in electric field now points from the metal, which is positively charged because it loses the electrons, towards the negative space charge region of the p-type semiconductor. Okay, so the role of the built-in field is exactly the same, is to stop the transfer of charge at thermal equilibrium. So at thermal equilibrium, the two Fermi levels in the metal and the p-type semiconductor, they align. Okay, and there will be a built-in field, therefore there will be a gradient, right, inside the Venn diagram here. Okay, so this is this Venn diagram in the p-type semiconductor bend downwards like this. Okay, giving you a positive gradient, which is self-consistent with the positive electric field, which we have in this case. All right, this is a positive electric field pointing in a positive x direction. Okay. All right. So we can also form a Schottky contact on the p-type semiconductor. All right. What about the built-in voltage? It is evaluated in the same way. All right. It can be evaluated by taking the difference between the two work functions, which essentially gives you the difference between the two Fermi level at the beginning of contact formation. So this is the built-in voltage, okay, QV naught, which is now Q phi S minus Q phi M, right? Because in this case, the semiconductor work function is larger than the metal work function, okay? All right, so it is a built-in voltage that prevents the transfer of electrons from the metal to the semiconductor, okay? Right, because the associated built-in electric field will tend to pull back the electrons, right? Pull back the electrons towards the metal. Okay, so stopping the transfer of the electrons from the metal to the p-type semiconductor. So this is a Venn diagram under thermal equilibrium condition. Right. Okay. So let's quickly go through what happens under external voltage biasing. Right. In this case, forward bias is achieved by applying a positive voltage to the p-type semiconductor with respect to the metal. It is different from the other example. Remember in the earlier example where we had Schottky contact on an n-type semiconductor, to forward bias it, we apply a positive voltage to the metal with respect to the n-type semiconductor. In this case, it is the opposite. So why it is like this, right? One easy way to understand this is that under forward biasing, the voltage that we apply is opposing the built-in voltage. Okay, so in this case, forward biasing, we want to make the p-type semiconductor region more positive with respect to the metal, so that the applied voltage opposes the built-in voltage, which is in the opposite direction. Okay, so under forward biasing, therefore, we make the p-type semiconductor more positive with respect to the metal. And the applied electric field now points from right to left or in the negative x direction, right, opposing the built-in, which points from left to right or in the positive x direction. So the net electric field across the junction is reduced, which is also manifested as a reduction in the barrier height across the contact. Okay, all right. So with the reduction in the barrier height, right, electrons in the metal can easily move to the valence band of the p-type semiconductor. All right, eliminating the holes in the p-type semiconductor. So we get electron injection from the metal into the p-type semiconductor under forward bias. So the contact can conduct a large current. All right, under forward bias. So what happens under reverse bias? So the applied voltage is reversed, right? So now the positive voltage get applied to the metal, and the negative to the to the p-type semiconductor. Okay, so this is the Venn diagram. All right, so since the metal is now more positive with respect to the p-type semiconductor, so the Venn diagram on the metal side move downwards relative to the Venn diagram on the p-type semiconductor side. Right, so this relative movement also result in the increase in the potential barrier height. All right, across the contact. Okay, all right, so that blocks the electron transfer from the metal to the valence band of the p-type semiconductor. Okay, remember under thermal equilibrium, this electron in the metal are already blocked by the built-in potential barrier. So here we are enhancing it, so they are further blocked. Okay, all right. Now, on the other hand, right, electrons in the valence band of the p-type semiconductor, they themselves also cannot easily get to the empty states in the metal because these electrons in the valence band of the p-type semiconductor, they face a barrier. And this is the Schottky barrier for the p-type Schottky contact. Notice that it is evaluated differently from the Schottky contact of the n-type semiconductor. Okay, so in this case, the Schottky barrier is the difference between the Fermi level in the metal and the valence band HEV of the semiconductor. It shows a barrier height that electrons in the valence band of the p-type semiconductor face in going to the empty states in the metal. All right, okay, so therefore this difference is can be calculated by taking the difference between the work function of the metal, Q phi m, and this Q chi plus QEG. All right, okay, so Q chi, remember, is the energy difference between EC and the Fermi level. So if you take Q chi plus the band gap, all right, that will give you the energy of the valence band is EV. All right, if you take the difference, this will give you the Schottky barrier height in this p-type semiconductor contact. Sorry, p-type. Okay, maybe the earlier diagram is clearer. All right, so this is a Schottky barrier. The difference between the Fermi level here and the EV in the semiconductor. So the EV in the semiconductor can be evaluated by taking the sum of Q chi and the band gap. Okay, so if you take this minus away the work function of the metal, we get the difference between EFM and EV. All right, so this gives me a barrier that prevents electrons in the valence band of the p-type semiconductor going to the empty states in the metal. All right, so the Schottky barrier, likewise, in this case, limit the magnitude of the reverse leakage current flow. All right, okay, so the concepts are very similar, but we need to make some minor modification to some of the expression here, in particular the Schottky barrier expression. Okay, all right. Okay, I think it's a good time to go for the break. So I will stop here for the break. Let's go for a 10-minute break, and then so what's the time now? The time now is about 5:20 p.m. So okay, let's go for a 15-minute break. Okay, so let's come back by 5:35. All right. In the meantime, I will still be online. So if you have any question, you can ask. Feel free to ask. Okay.
Hi, Professor. Hi, Professor.
Yes. Yeah, I'm around.
May I ask, for the Schottky barrier, can we understand it as like, because like metal and the semiconductor are two different systems, so the electron, in order for them to move into the semiconductor, they must like remove themselves from one system before they can enter the other.
Okay, but this understanding is not exactly correct. Well, in the sense that the electron need not remove themselves. All right. Okay. I mean, if you want to think of it that way, I don't think conceptually is very wrong. So if you go to this example, earlier example, maybe. So for example, if you want an electron in the metal to move to the N-type semiconductor, this electron can first go to the vacuum level, and then from the vacuum level, it goes down into the N-type semiconductor. Okay, from that perspective, yes, that would be the barrier that the electron have to face, because that would be the difference in the energy that you need to provide to remove an electron from the metal to the vacuum level. But the electron will gain energy, right? So this is a positive work done. This is a negative work done. So the difference between the two energy will give you the barrier that the electron face, right? Going from the metal to the N-type semiconductor. That is a conceptual visualization, which I think is fine.
Okay. And another question is, for because the when the before the equilibrium is reached, the electron move from the semiconductor into the metal, right?
Yes.
It means that there are charges stored inside the metal. Why the electric field not in the metal not counted?
Oh, okay. Yeah, that's a very good question, right? In fact, we do not consider the electric field in the metal. In fact, in a perfect metal, there shouldn't be any electric field. Okay, the reason is because in a perfect metal, there's a high density of electrons, right? Inside the metal, any additional electron that you add to the metal cannot penetrate into the metal. They can only exist at the surface of the metal.
Yes.
Right, so there is no internal electric field inside the metal. All right, so in this example, it is not very correct to draw the electrons at this position here. In fact, the electrons are not here, but they are exactly held at the interface between the metal and the semiconductor.
Okay.
Right, they're at the surface of the metal.
But since the electrons are accumulated at the surface, doesn't it mean that there are still electric field at the surface of the contact?
Yes, there is electric field at the surface of the contact. In fact, this electric field is maximum. Remember, in the case of p-n junction theory, remember we said that the maximum built-in field exists at the metallurgical junction. So in this case, the metallurgical junction is here, which is the physical boundary between the metal and the semiconductor. This is a hetero junction, actually, right? It's a junction between two different materials. So the metallurgical junction is actually the physical boundary. So in this case, the maximum built-in electric field exists at the metallurgical junction. There is an electric field here. It's just that the electric field drops very quickly to zero the moment you move into the metal by an infinitely small distance into the metal.
But when we are calculating the voltage drop, does it mean that we are also taking into account of the negative charge on the metal surface?
Yes, yes. The voltage difference between the metal and the semiconductor is given by the area under the built-in electric field plot, right?
Yes.
So in this case, you can imagine. Okay, I don't have. Okay, I don't know whether I can draw anything out of this cursor.
Does it mean that the distance of the electric field in the metal is not can be is negligible?
It's zero. There is no electric field in the metal. So if you try to
at the surface,
at the surface is the maximum electric field. So let me try to see. Okay. See if I can open up the electric field plot for PN junction. I just want to borrow a diagram here, right? But the diagram is not exactly the same as the diagram I'm going to show you, but I will tell you the differences. So what essentially I'm trying to say is that if you are trying to draw the electric field distribution plot for the metal semiconductor Schottky contact, so the plot that you get should look something like this, but not the same. Huh? So essentially, imagine now this is a metal, okay? So this is an N-type semiconductor. So if you want to draw how the electric field vary with distance, all right, on the N side is exactly the same. So the electric field is zero in the neutral N region, and it rises linearly in the space charge region if you apply depletion approximation, neglecting the concentration of carriers inside the depletion region. Or in other words, you consider only the doping ions inside the depletion region. So the electric field will vary linearly. And then you will reach a maximum at the metal semiconductor interface here. And the moment you step into the metal, the electric field drops abruptly to zero. So in fact, it's a right angle triangle if you want to draw the electric field distribution plot. So the electric field reaches a maximum here, and it instantaneously drops abruptly towards zero the moment you cross into the metal.
Okay, I see. Yeah, thank you.
All right, guys, time to come back and resume our discussion. Okay, just to do a sound check again before I continue. I hope it is okay. Nothing has changed. All right, if something has changed, please let me know. All right, so let's continue with the discussion on metal semiconductor contact. So we are done with the Schottky contact. Now, the next topic that I'm going to move on will be ohmic contact. So I will begin with an example for the N-type semiconductor. So to get an ohmic contact on an N-type semiconductor, the metal that I use need to have a work function smaller than the N-type semiconductor. All right, this is important because in this case, all right, since the Fermi level in the metal is higher than that in the semiconductor, electrons are filled to higher energy states in the metal compared to the semiconductor. Upon contact, these electrons in the metal situated at higher energy level will get transferred to the conduction band of the N-type semiconductor. Notice in this case, the direction of electron transfer is exactly opposite to the case of the Schottky contact. All right, remember in the earlier case, the Schottky contact, the electrons are transferred from the semiconductor, N-type semiconductor to the metal. Now, since the N-type semiconductor in this case receives electron, it becomes negatively charged. All right, and the metal which loses electron becomes positively charged. And a built-in electric field also exists across the contact. And the built-in electric field has the same role to play in the sense that it tries to stop the transfer of the electrons eventually at thermal equilibrium. All right, now, first difference between the ohmic contact and the Schottky contact is that the N-type semiconductor here does not lose electron. All right, it gains electron from the metal, and therefore, in the ohmic contact, there is no space charge region formed in the N-type semiconductor. All right. In fact, the excess electrons that the semiconductor gain from the metal, they pile up at the contact or at the interface here at the metallurgical junction here, right? And these excess electrons are held by the positive, the net positive charges inside the metal. Okay, all right. So in this particular example here, we do not get a space charge region. In other words, we don't have a highly resistive region present in the semiconductor. In fact, the excess electrons that pile up at the metallurgical junction here will make the region of the N-type semiconductor here even more conductive than the rest of the N-type semiconductor region. Okay, all right, so this is an important point to keep in mind. Now, how do we draw the energy band diagram of this contact at thermal equilibrium? Very similar concept. In fact, almost the same. The Fermi level of the two materials must be aligned at thermal equilibrium. And since there is a built-in electric field that points from the metal to the semiconductor, so this built-in electric field will correspond to a positive gradient, right? Because this built-in electric field points in the positive x direction, so it's a positive built-in field, all right? So it corresponds to a positive gradient in the energy band bending of the energy band in the semiconductor. So the energy band in the semiconductor bend downwards like this to give you a positive gradient. Alternatively and self-consistently, since the N-type semiconductor region now has excess electron piling up here at the metallurgical junction. All right. In other words, the concentration of the electrons here will be higher than the rest of the N-type semiconductor region. And therefore, the separation between EC and EFS, the Fermi level in the semiconductor, is smaller here than in the rest of the semiconductor region. Okay, so that's a Venn diagram of ohmic contact under thermal equilibrium. All right. Now, we can also evaluate the built-in potential, right, in a similar way. Right, so in this case, the built-in potential is given by the initial difference in the two Fermi level, which can be evaluated by the difference in the two work function, right? So in this case, we take Q phi S, which is a work function of the semiconductor, minus away Q phi M, the work function of the metal. Okay, so that will give us the built-in voltage across the ohmic contact. And in this case, all right, although the concept of Schottky barrier is no longer relevant, but if we try to define it in a Schottky barrier in this ohmic contact case, in fact, we will end up with a negative Schottky barrier. All right, we'll end up with a negative Schottky barrier. So basically, in this particular contact, the electrons in the metal do not face any barrier in going to the N-type semiconductor. Right, okay. Of course, after the charge transfer has happened, there will be a small barrier that stops the flow of the electrons from the metal to the N-type semiconductor. Okay. Just keep in mind that the concept of Schottky barrier does not apply here in this case. Okay, all right. All right, just to recap what we have discussed. So at the instant of contact, since electrons are filled to higher energy levels in the metal, these electrons see no barrier in crossing to the conduction band of the N-type semiconductor. So they get easily transferred across to take up the lower energy states in the conduction band of the N-type semiconductor. So as a result of this charge transfer, okay, you get the built-in voltage and the built-in electric field setup. Now, notice that electrons in the semiconductor see a barrier in crossing into the metal. Okay, all right. So if you apply the concept of Schottky barrier, it's a negative Schottky barrier, but this negative barrier actually applies to the electrons in the semiconductor, right? So the electron in the semiconductor see a barrier going to the metal, right? So during contact formation, electrons are not transferred from the semiconductor to the metal. On the other hand, electrons are transferred from the metal to the semiconductor. Okay, so there'll be a net transfer of electron from the metal to the semiconductor, and the excess electron charge in the N-type semiconductor essentially exists as a surface charge density. So what that means is that essentially these excess electrons are held very close to the metallurgical junction in the form of a layer of negative charges, all right, like a surface charge, all right, existing at the metallurgical contact. At the metallurgical junction, all right, okay. So we can describe it like this. So the N-type semiconductor will therefore have an accumulation of electrons. Remember, electrons in the N-type semiconductor are majority carriers, right? Okay, so these electrons are accumulated near the surface at the contact region. Okay, right. On the other hand, due to the loss of electron, the metal will have a layer of net positive charge, also held very close to the surface here of the contact. Okay, all right. So what is the main difference between metal N-type semiconductor Schottky and ohmic contact? We will address this next. Okay, so since due to the transfer of charges, there'll be a potential difference across the metal and semiconductor, and there'll be energy barrier that eventually reduces and entirely stop the flow of electrons from the metal to the semiconductor. Okay, so thermal equilibrium is achieved when the rates of electron flow in both directions are exactly balanced. All right, in other words, when the electrons that get transferred from the metal to the semiconductor, they backflow into the metal again. All right, so the net transfer of charge is 0 across the junction at thermal equilibrium. Okay, all right, so just take note of the difference. The main difference here is that although charge transfer still happens, all right, and the charge transfer would result in the potential difference and the built-in field across the contact, similar to the Schottky contact case. But the major difference here is that there is no space charge region formed in the N-type semiconductor. Okay, all right. So all right, so from the energy band diagram at thermal equilibrium, one can see that there's an energy barrier formed that prevents the electron, right, from the metal crossing into the semiconductor. Okay, this energy barrier is actually given by the difference between EC and EF in the semiconductor, right, which is from here, because the electrons are filled up to this level in the metal. So this electron will see a barrier, right, of EC minus EFS before they can get into the N-type semiconductor, right? This is the main difference which I've just mentioned. All right, so this is a Schottky contact on the N-type semiconductor, and this is a ohmic contact on the N-type semiconductor as well. Right, so in the case of a Schottky contact, there is a depletion region formed. Now, this depletion region is very important in playing the role of rectifying contact. All right, so essentially it separates the conducting electrons in the metal from those in the semiconductor. All right. And for the ohmic contact, there is no such depletion region. In fact, there is accumulation of excess electrons in the semiconductor near the contact. And therefore, the conducting electrons in both material are not physically separated. In fact, they are very close to each other. All right, they are very close to each other at the contact. So this makes this particular contact a very conductive contact. Okay, so the contact is a conductive region. Unlike in the case of Schottky contact, you have a depletion region, which is a highly resistive region, separating the electrons in the two materials, the metal and the semiconductor. But in the case of ohmic contact, there is no such depletion region. So the electrons in the N-type semiconductor and those in the metal are actually next to one another, literally. Okay, right? And because of this major difference, the IV behavior or the IV curve of the two contacts are entirely different. Okay, we'll come to that shortly. So it can be seen that there is no barrier for electron moving from semiconductor to the metal. Okay, all right. But there is an energy barrier preventing electrons in the metal going to the semiconductor. This energy barrier is set up because of the earlier charge transfer that happens. Okay, that creates a built-in voltage. And the barrier for electrons located at the Fermi level of the metal is this. It can be quantified as Q phi s minus Q chi, or it is the difference between EC and EFS. Okay, since Q phi s is Q chi plus EC minus EFS, therefore the difference between Q phi s and Q chi is EC minus EFS, which gives you the energy barrier that prevents electron located at the Fermi level of the metal going to the semiconductor. All right. Now, because the semiconductor is N-type, as we know, if we dope a semiconductor N-type, the Fermi level is very close to EC, and the heavier we dope the semiconductor, the closer would be the Fermi level from EC, right? Okay, so in fact, we can make the contact even more conductive by heavily doping the N-type semiconductor region. Okay, so in practice, we can dope the N-type semiconductor region more heavily, and in fact, this will further reduce the barrier that the electrons in the metal face going to the semiconductor. All right. Well, as you know, as you recall in part 1, you have learned that when you dope the N-type semiconductor region more heavily, the Fermi level will move even closer to EC. Right. Therefore, this will reduce the barrier that electrons in the metal see going to the semiconductor. So in doing so, it will make the contact even more conductive, right? Because the barrier is reduced. Okay, so one can say that essentially, therefore, there is negligible barrier for electron flow in both directions, and therefore, this is an ohmic contact. It is not rectifying, while in the sense that the contact allows current to flow easily in both directions. Okay, although strictly speaking, not the case. Sorry? Something wrong? What's wrong? What's wrong? Well, are you guys okay? I hope you're fine, because I heard something just now. I thought I accidentally muted myself again. That's why I came back to check. But all right, so I hope you're fine. Okay, so if I don't get any feedback from you guys, I will just continue. Right.
Hi,
Yeah.
Professor. Sorry, I got a question.
Yeah.
How about what happens? But if EC minus EFS becomes less than 3 kBt, then wouldn't it the semiconductor become a degenerate semiconductor? Or so does it matter whether the N-type semiconductor is a degenerate or non-degenerate kind for ohmic contact?
Yes, that is a very good question. In fact, it will be better if we have a degenerately doped semiconductor. In other words, the heavier the doping, the better. And intuitively, this is quite easy to see because, metal has a lot of electrons, right? So if we dope the N-type semiconductor very heavily, it also has a lot of electrons. So the two materials can conduct electricity very well. So putting them together, you can form a contact that has a very low resistance. And from the energy band diagram point of view, by doping the N-type semiconductor very heavily, the Fermi levels simply move closer and closer to EC. Yes, you will get a degenerately doped semiconductor. All right, and from the band diagram point of view, you can see that the energy barrier for electron to flow in both directions becomes becomes even smaller, right? Okay, so in fact, to answer your question, yes, it is better if we dope the N-type semiconductor degenerately. That means dope it very heavily. But of course, you need to be careful. If you dope the N-type semiconductor degenerately, then the difference between EC and EFS can no longer be accurately determined using the Maxwell-Boltzmann equation. All right, so that is the catch here. But well, other than this, yes, to dope it degenerately is better for the ohmic contact in terms of lowering the resistance. Okay.
Okay, thank you, Professor.
Hi,
Yeah.
when related to the previous question, you said that the semiconductor has to be degenerate. It's not only applies if the semiconductor or the
Your voice has broken up, I think, because of the connection. Can you repeat your question again?
oh yeah. So for because the previous question was about it being better if the semiconductor is doped degenerate.
Yes.
But this one only this one is under the assumption that the work function of the metal is higher than the work function of the semiconductor, right?
Yes, yes, it is still under the same assumption that in order to get ohmic contact, right, we still need the metal to have a work function smaller. Of course, in the limit, the work function of the metal can just be equal to the work function of the semiconductor. That will be fine as well. Okay, all right. So the reason for this is that because if we have a work function for the metal to be smaller than the semiconductor, electrons are still transferred from the metal to the semiconductor, and that will make the semiconductor region here even more conductive. That will help in lowering the resistance of the ohmic contact.
Okay, thank you.
Okay, so let's continue. So this is a thermal equilibrium case. So let's see what happens when we apply external voltage to the ohmic contact. Now here we don't really differentiate between forward and reverse bias. Of course, these two terms no longer apply in an ohmic contact because current can flow easily in both directions. So let's try to understand why current can flow easily in both directions in an ohmic contact. All right. So well, let us focus on the band diagram on the left. Now, in the band diagram on the left, all right, the voltage is applied in this way. Okay, we apply a positive voltage to the metal with respect to the N-type semiconductor. Now, notice that the band diagram that is drawn here is quite different from those you saw earlier for the ohmic contact. Okay, let me go back and try to refresh the memory a bit. You know, earlier we talked about the ohmic contact bias or reverse bias. All right, so let me bring back the here. Okay, remember, right? Under forward bias, we also apply a voltage, a positive voltage to the metal with respect to the N-type semiconductor. Notice that the Fermi level is drawn flat in the metal because we do not have electric field penetrating into the metal. All right. In the case of semiconductor, the energy band is drawn flat in the neutral semiconductor region because we also assume that there is no electric field present in here. All right. In other words, most of the applied voltage is dropped across the space charge region. Okay, changing the band bending within the space charge region. Now, this assumption is obviously no longer applicable in the ohmic contact because in the ohmic contact, we do not have a space charge region, which is a highly resistive region. So therefore, in the ohmic contact, the applied voltage must be dropped across a certain region. Okay, so let me go back. All right, so let's consider the two regions. Right, the metal is definitely more conductive than the N-type semiconductor. Right, so it is reasonable to continue assuming that there is no voltage drop across the metal. All right, okay, but the voltage has to drop, therefore, across the semiconductor. So in drawing the band diagram of the semiconductor, we cannot assume the band to be flat anymore, right? Because there's an electric field that is developed across the entire N-type semiconductor due to the applied voltage. And since there's an electric field, there would be a gradient in the energy band diagram of the semiconductor. All right, so that's why in drawing the band diagram of an ohmic contact in this example, when a positive voltage is applied to the metal, a negative to the N-type semiconductor, the band diagram on the negative end of the, at the end of the N-type semiconductor here is raised with respect to the Fermi level in the metal. Okay, how much this band diagram on the semiconductor is raised would depend on the magnitude of the applied voltage. Of course, if you apply a stronger voltage, the band diagram is raised more, which corresponds to a higher slope in the energy band diagram. All right, and this cell consistently translate into a higher electric field across the N-type semiconductor. Okay, so there's one point that you need to take note. Now, the second point is that if we apply the voltage in this manner, you can easily see that there is practically no barrier preventing electrons in the N-type semiconductor flowing to the metal, as shown by the arrow here. Okay, so if you apply an external voltage this way, electrons can easily flow from the metal to the, from the N-type semiconductor to the metal. All right, so the ohmic contact allows current to flow easily if you apply the voltage in this manner. All right. Now, on the other hand, if you reverse the polarity of the voltage, so in this diagram B, so what we do is that we apply a positive voltage to the N-type semiconductor with respect to the metal. Okay, so since we make the N-type semiconductor more positive, the energy band here, all right, of the N-type semiconductor is pulled downwards relative to the Fermi level in the metal. Okay, all right. Now, as you can see in this case, there is also practically no energy barrier preventing electrons in the metal flowing to the N-type semiconductor. Of course, strictly speaking, there is a barrier, but this barrier is very small. Right? It's this little hump here that you see here. Okay, so since this barrier is very small, electrons in the metal can also easily flow into the N-type semiconductor, all right, giving a large current flow as well if you reverse the polarity of the external voltage. So as you can see, this contact allows current to flow easily in both directions, and therefore it doesn't have a rectifying property. All right, so it is called an ohmic contact. In other words, it's called a resistive contact, and the resistance of such a contact actually mostly comes from the semiconductor itself. Right, okay. Okay, just to summarize, when a positive voltage is applied to the metal, electrons can flow downhill. Well, in a sense, I mean, this is just a way to describe this diagram. As you can see, the electrons are like rolling downhill, okay, from the Venn diagram of the N-type semiconductors, which is raised up with respect to the Fermi level. Okay, right. On the other hand, when a positive voltage is applied to the semiconductor, well, electrons can also easily flow from the metal into the semiconductor because there is only a very small barrier, right, at the contact. And this barrier can be even made smaller by increasing the doping concentration of the N-type semiconductor. We were talking about it, right? When you dope the N-type semiconductor more heavily, the EF, S, and the EC will get closer to each other. That will further reduce the barrier that electrons in the metal face when they try to get to the N-type semiconductor. Okay. All right, so therefore this contact is called an ohmic contact. Now, why are ohmic contacts needed? Well, I mentioned briefly at the beginning, because we need to connect semiconductor devices together, and as well as connecting them to other parts of the circuits. So ohmic contacts are needed in a sense, so they are formed during the fabrication of the IC chip. Just to give you a flavor of what exactly is like inside the IC chip. So if you look at this diagram here, it is an electron microscope picture. Okay, why do we need to use an electron microscope now? As you know, a conventional microscope works based on visible light, but the wavelength of the visible light is rather big. Remember, if you check the visible spectrum, the wavelength actually ranges from 400 nanometer at the blue end to about 700 nanometer at the red end. Okay, so this wavelength of 400 to 700 nanometer is huge compared to the dimension of the features that we built in the integrated circuit. For example, the features that you see here, these lines are actually metal lines. Okay, these are metal lines connecting some part of the circuit to another part of the circuit. Right. So these metal lines will form ohmic contact to the semiconductor devices in the IC chip, connecting them together. Now these metal lines have a dimension much smaller than the wavelength of visible light. In fact, for state-of-the-art technology like what we are doing today for the microprocessor chip and so on and so forth, the dimension of these lines could be just around 10 nanometer or even smaller. Right, 10 nanometer is significantly smaller than the wavelength of visible light. So a conventional microscope is not able to, or a conventional microscope cannot allow us to view these features clearly due to the diffraction, Rayleigh's diffraction phenomenon. Okay, so the image will be totally blurred. We could not see anything if we use a conventional microscope. All right, so we have to use an electron microscope. Why an electron microscope can help us image very small dimension? Because electron wavelengths can be very small, can be much smaller than the feature size that we are having here. Okay, so that explains the picture itself. This is the electron microscope picture. Okay, so the lines that you see here are metal lines. All right. What are these cylindrical objects that you see here? These are what we call vias. So via is also a metal, all right, serving to connect metal line at one level to the metal line at another level. All right, so what you see here is if you look at this feature here, this is a metal line at level 3. Okay, so a metal line at level 3 can be connected to another metal line at a higher level at level 4 through a via like this. Now, why do we need different levels of metal line in an IC chip? Now, if you take, for example, a modern microprocessor, inside this micro P, like the Intel micro P, there are several billions of semiconductor devices. Not millions, billions. So there are several billions of semiconductor devices. So in order to wire all these devices up together to form circuits that do certain work for us, right, we need several layers or levels of metal lines. Okay, right. So this is just to give you a flavor of what is going on in actually, well, I mean, what is actually going on in real IC chip. Okay. Now, in order to wire the semiconductor devices together, obviously we cannot afford to have Schottky contact because the Schottky contact has a diode-like behavior. By introducing a Schottky contact, you introduce additional diodes into your circuit. So obviously the functionality of the circuit would not be the same as what you intend them to be. Okay, right? So to make all the connection, we need the contact to be ohmic and having minimal resistance, all right, so that the signal do not get rectified during the circuit function. Okay. So a practical way of forming the ohmic contact is by doping the semiconductor heavily. Yeah, this question was asked earlier. Yes. In fact, we want to dope the semiconductor heavily when we want to have good ohmic contact. So what do I mean by good ohmic contact? A good ohmic contact is one that has a very low contact resistance. Okay, so in doping the semiconductor more heavily, it reduces the barrier that electrons in the metal see when they flow to the semiconductor. Remember, we are still talking about N-type ohmic contact. We haven't come to P-type ohmic contact. Okay, right. So, for example, okay, we have studied PN junction diode. So how do we connect PN junction diode to other parts of the circuitry? Okay, so what we normally do is that we dope a certain region in the P and a certain region in the N very heavily to create a P plus and an N plus layer. All right, so in doing so, we can put metal onto the P plus and the N plus layer, forming ohmic contact. Okay, so to complete the discussion, so let's see what happens in ohmic contact form on the P-type semiconductor, right? Okay, to form an ohmic contact on a p-type semiconductor, the metal that we use should have a work function that is larger than that of the p-type semiconductor. All right, so when the two material come into contact, what essentially happens is that electrons from the valence band of the p-type semiconductor are transferred to the metal. All right. So what happens when electrons are lost from the valence band of the p-type semiconductor? You get more holes created. Right. So the semiconductor gain more holes. Right. And these holes pile up at the contact interface here, held by the electrons which the metal gain from the p-type semiconductor. All right. So making this region of the p-type semiconductor even more conductive compared to the rest of the p-type semiconductor region. Okay, so so this is the band diagram at thermal equilibrium, right, where the two Fermi levels are aligned. Okay, so the energy band on the p-type semiconductor bend upwards like this, right, giving you a negative gradient consistent with the direction of the built-in field, which points from right to left or in the negative x direction. So the built-in voltage can also be evaluated, right, by taking the initial difference between the two Fermi levels. Okay, so the concepts are very similar, so I only briefly go through them here for the p-type ohmic contact. Okay, so let's see what happens when we apply a voltage to the p-type ohmic contact, whether there are any barriers that prevent the flow of charges. Well, as you would have guessed, very small, practically there is no barrier preventing the flow of charges in both directions. Okay, so the diagram that you see on the left correspond to the case where you apply a positive voltage to the metal with respect to the p-type semiconductor. Now, earlier on, I call this forward bias, but you can neglect this if you do not wish to consider this, because as I mentioned, the forward and reverse bias terms are no longer applicable in the ohmic contact. But why I can still call this forward bias, well, simply is based on the semiconductor. I mean, based on the PN junction example that we had. Remember, under forward bias, the applied electric field opposes the built-in field. So in this example, the built-in field points from the semiconductor towards the metal. And if I make the metal more positive with respect to the p-type semiconductor, I'm applying a electric field that opposes the built-in field. So I call that forward bias. But this is not essential in this case. Okay. So what happened under forward bias? Remember, the same thing will happen in this case. The energy band diagram will be in the p-type semiconductor will be raised up relative to the EFM in the metal. All right. Why this is the case? The same reasoning, because the metal is more conductive than the p-type semiconductor, so the applied voltage must be dropped across the p-type semiconductor, right? So creating electric field in it, which explains the gradient in the energy band. All right, so in this case, as you can see, under this forward biasing or this manner of applying an external voltage, electrons from the valence band can easily flow to the metal. Okay, right. Now, if you reverse bias the, if you interchange the positive and the negative terminal of the battery source, so the band diagram will look like this. So in this case, the energy band on the semiconductor side will now be pulled down relative to the metal, because now the P semiconductor is more positive with respect to the metal. Right, so in this case, there is also no barrier preventing electrons in the metal flowing to the valence band of the p-type semiconductor. Okay, so this gives an ohmic contact behavior. Okay, at this point, I think the picture is more complete. Remember, in the earlier discussion on PN junction, we talk about forward bias and reverse bias. And in order to achieve that, we actually need to form metal contacts at the end of the P region and the N region. all right? And these contacts need to be ohmic contact. Okay, so with this discussion on ohmic contact, now I think you can have a more complete picture as to how the charges flow in the circuit. Like for example, in the forward bias circuit, some of you actually asked me, where do the electrons come from and where do the holes come from? You know, under forward bias, when we mention about electron hole injection across the PN junction, where do the electrons and the holes come from? They are provided through the ohmic contact. Okay, so if you look at the N-type ohmic contact that we saw earlier, okay, all right. So imagine, you know, this to be the N region of a PN junction, right? So this is the N region of a PN junction. The P side is here, which is not shown, of course, in this case. So during forward bias, we make the P region more positive with respect to the N. Okay, so the energy band diagram will now be put down like this on the N side, which allows electrons to be easily supplied from the metal to the N-type semiconductor. Okay, all right. So if you go to look at the P-type semiconductor, so during forward biasing of the PN junction, we apply a positive voltage to the P-type semiconductor. So relative to the metal, all right, as you can see, the positive voltage that you apply to the P-type semiconductor will cause the metal, all right, band diagram to move downwards relative to the P-type semiconductor, all right. So that facilitates the flow of valence band electron from the P-type semiconductor to the metal. So when electrons leave the valence band, you get more holes. So these holes will flow to the rest of the P-type semiconductor region. All right, and these holes will get injected to the N side under forward bias case. All right, so that's how the continuity of the charge flow can be maintained in the forward bias PN junction diode. Okay. Right, so to summarize, if you want to form an ohmic contact on N-type semiconductor, the work function of the metal you choose should be smaller than the N-type semiconductor. In doing so, you result in electron being transferred from the metal to the N-type semiconductor, making the N-type semiconductor even more conductive. On the other hand, if you want to form an ohmic contact on a P-type semiconductor, the metal should have a larger work function. So in this case, electrons are transferred from the valence band of the P-type semiconductor to the metal, creating more holes in the P-type semiconductor, making the P-type semiconductor more conductive. Okay, all right. Okay, as a summary, all right, so there are 4 different types of contact. All right, you have Schottky and ohmic, and in each case, the contact can be formed on either N-type or P-type semiconductor. So in total, you have 4 different types of contact: 2 Schottky contact and 2 ohmic contact. Okay, all right. So notice that depletion regions are formed in the Schottky contact, and accumulation of majority carriers occur in the ohmic contact. Okay, so this is a major distinction between the 2 different types of contact, and also the major reason why the electrical behavior of the 2 contacts are totally different. All right, one is rectifying, the other one is basically a simple resistor with very low resistance. Okay. All right, so that's about all we have for today. So it's about time to end here. I'm still available for questions in case you have any. All right, so now it's open for question. Yeah.
Am I audible?
Sorry again, I can't hear you very well because there is some interruption.
Can you hear me now?
Oh yeah, I can.
Okay. Because I mean, it's not just the application, an application, but when we say that we had to use its degenerate semiconductor when.
Sorry. Can you repeat your question because you are breaking up again?
Okay. When you say that we have to use a degenerate semiconductor when forming an ohmic contact.
Yes.
Does that mean that there has to be some form of uh, a difference in the concentration of dopants when we are creating the PN and the when you're creating a PN junction that's connected via metal lines?
Yes, for example, okay, let me borrow a diagram. I don't know whether I can, yeah, yeah, okay, so case, yeah, okay, yeah, right. So you have P and N region. So in order to connect the PN junction to an external circuit such as a battery source, we need to form an ohmic contact here and an ohmic contact here. Now, you don't get good ohmic contact if you leave the P and N region moderately doped. So what people normally do is that to form an ohmic contact, we convert one small part of this P region into a highly doped P region or P plus doping. Similarly, we convert a small part of this N region into a highly doped N or N plus region. Okay, so after doing that, then we can put the metal, right, to form the ohmic contact. Does that answer your question?
Yes, kind of. But that leads on to my second question. It's like,
Yeah.
so if there's one small region that's more dope than the other, would that mean that there's changing conduction and the conduction band energy within the same side of the semi?
Oh yes, yes. I think I understand your question. Although your speech broke up quite a bit just now. Okay, essentially your question is that if I convert part of this P region into a heavily doped P region, would there be a difference in the energy band diagram between the P plus and the P? Is that your question?
Yes.
Yeah, there is, right? There would be. The same concept applies. The same concept applies. All right. So imagine you have two P regions. One is heavily doped. The other one is not so heavily doped. So initially the Fermi levels are different. Okay. So when the two regions come into so-called contact to form contact at thermal equilibrium, alignment of the two Fermi levels would happen, and this alignment will cause. I mean, this alignment is also driven by a charge transfer, right, between the two differently doped regions, and there would be an electric field and a built-in voltage form across these two regions. But the interaction that you see here between the P and the P plus region will give you an ohmic contact as well. So in other words, the P plus region will form an ohmic contact with a P region. You can think of a P plus acting like a metal, forming an ohmic contact with the P region. Right? There is no contradiction in the concept if you go back to the P-type semiconductor. I mean P-type. To form a P-type ohmic contact, we need to choose a metal whose work function is larger than the P-type semiconductor. In other words, to begin with, the Fermi level in the metal has to be lower than the Fermi level in the P-type semiconductor. So now imagine this metal has become a P plus semiconductor. So in the P plus semiconductor, the Fermi level is lower than the Fermi level in the moderately doped P-type semiconductor. So these two will also form an ohmic contact.
Okay, I understand. Thank you.
Right. Any other questions? Okay, so to study this topic, I would say is not as difficult as the PN junction because some of the concepts are very similar. So you just need to look out for the newer concepts like work function, electron affinity, you know, and then to apply them accordingly, and you should be fine. Okay. All right. So if you have no question, then we'll call it a day. We don't want to be hanging around waiting for each other. So have a good weekend. So this is a long weekend. So I think tomorrow is a public holiday for everybody. Okay. All right. So have a good long weekend, and I'll see you next. I will see some of you on next Monday. Okay. All right. So in the meantime, if you have questions, feel free to email me. When you email me, please also be more specific about your question. Okay. All right. That is important because if I don't understand your question, then I cannot answer it properly. All right. So you need to be more specific about the question that you send. Okay. All right. Okay, so see you guys. Thank you very much, and have a good weekend.
Thank you, sir.
Okay, thanks, bro.
Thank you, Prof.
Thank you, Professor.
Thank you, Prof.
Thank you, Prof.
Thank you, Prof.
Okay, yeah, thanks a lot, and stay safe and have a good weekend.